All right. Hello, everybody. Um, what we have here are some extra problems to get practice solving systems with Gaussian elimination if you need it. This is totally optional. I know there's a few people in the class. There's a good few people who are struggling with this a little bit, who might need to get a little extra practice because it is going to be an important skill. This is one of the main things we're going to be doing in the class. Uh, now, let's see. Now, I wanted to remind you of a few things. I'm going to do a couple examples just to sort of illustrate what I mean. Uh, I want you guys to try to use this strategy here to try to follow these steps. The reason is that if you're using other methods, other strategies like substitution, that's not really going to help you in the rest of the class because everything we do from section 1.2 onwards is going to be like in terms of the results you get from doing this process with elimination, not with substitution or anything. So it's not much use to practice the substitution method, for example. So yeah, let's and I put the elimination methods here, the strategy, just so it's in your line of sight, and the elimination operations here, just so you can reference them. So I'd like to do a couple of these just to remind you of some things about the strategy. Let's look at number one first. So we're gonna eliminate this as much as possible, reduce it completely, following the strategy, and see if it's consistent and how many solutions it has, and if it has a unique solution, find it. So yeah, and as we do this, maybe let's just look at the steps. The first equation says if the top equation doesn't have x1, u swaps to get it there. Scale the top equation so the coefficient of x1 is 1. Okay, that's already done. We already have a 1 x1, so that's fine. Use multata placement to clear all the x1 terms below it, but there are no x1 terms from in the other equation, so that's done. Step 3 says if the second equation doesn't have x2, use swaps to get it there, but it already has x2. Scale the second equation so that the coefficient of x2 is 1. That's already done. Then step 4, use multata placements to clear all the x2 terms from the other equations. So that means clear away this x2. Okay, so to do that, we want to take this negative 3x2 and add x2, add 3x2 to it. So we're going to replace each side of one equation by the sum of itself and a multiple of the other equation's sides. And the equation we want to replace is equation 1. So equation 1 will now be equation 1 plus 3 times equation 2. And equation 2 is going to be left alone. And I want to emphasize it's a good idea to write the whole system with every step. So don't just leave equation 2 hanging out over here, but write the whole system. So equation 1, after this operation, is going to be the left side of equation 1 minus 3x2, and then that plus 3 times x2, because we're adding 3 times the both sides of the second equation, and that would be equal to negative 12, what we had before, plus 3 times 5. And usually we're not going to write this step because like we can just see, okay, we're doing negative 3x2 plus 3 times x2. You know that's going to be 0. That was the whole point. So you can just write this as plus 0 if you want. And then on the other side here, negative 12 plus 15 is 3. Okay, so there's a system of equations that is equivalent to uh, the original system, and this one clearly has x1 equal to 3 and x2 equal to 5, so it is consistent with a unique solution 3 comma 5. So yeah, we follow the steps, we got there. And notice that like we were essentially adding 15 to both sides of the first equation. That's the same thing you would get if you took this x2 and replaced it with 5. You would have like x1 minus 15 here, and then you would add the 15 to both sides and still get x1 equals 3. So it gives you the same thing, but I want you to know how to do it using multata placement instead of substitution. Okay, so that's one of them. Let's look at another one. Let's look at number 7 here. So, zoom out a little so we can see the steps and the problem. Okay, so if the top equation doesn't have x1, use swaps to get it there first. Okay, so we need to do that. We can swap equation 1 and equation 2 to get this x1 where we want it. So we're going to do and this is now going to look like x1 plus 3x2 equals 2. The second equation is negative x2 minus x3 equals 0. And the third equation doesn't change. Okay, so it doesn't take too long to write out the whole system again, and this way we're keeping track of what all the equations are. So now the coefficient of x1 in the top equation is 1, so we're done with step 1. Step 2 says use multata placements to clear all the x1 terms from the other equation. So we want to get rid of this 4x1 here. So we can do that by doing 4x1 minus 4 times x1. That would give you a 0x1. That would be eliminating that x1. So let's do that. We want to replace equation 3 with the sum of itself and minus 4 times equation 1. And the first two equations are staying the same. So we're just going to write them again. And the third equation now, I'm not actually going to write out this whole thing minus 4 times this whole thing. Let's just, no, we're going to distribute the minus 4 into it and then combine the like terms and do it all at once. So 4x1 minus 4x1 is 0. That was the whole reason we did that. Then we have 13x2 minus 4 times 3x2. So 13x2 minus 12x2 is plus 1x2. And then we have x3 minus 4 times 0x3, so that's just x3. But then we have 8 minus 4 times 2, that is 0. Now we have a system of equations that's still equivalent to the previous one. Okay, so that's good. Let's see what's next in the steps. We are now on step 3, which says if the second equation doesn't have x2, use swaps to get it there. Okay, so the second equation does have x2. Then so we don't have to swap anything. We can scale the second equation, so the coefficient of x2 is 1. And this one, you're going to see it's not really necessary here, but we might as well do it. So we're just going to do equation 2 scaled by -1. The first equation is unchanged. We have now 1x2 plus 1x3. So now we have a coefficient of 1 there. And then the third equation is 1x2 plus 1x3 equals 0. And so that's our new system, just following the steps exactly. Now we can use multidata placements to clear the x2 terms from the other equations. And if you want to clear away this 3x2 and this x2 in equations 1 and 3 at the same time, you can do that. Or we can see the important thing is going to happen in equation 3. So maybe let's just do that one. So we want to take equation 3 and replace it with the sum of itself and -1 times equation 2. And the goal is we want to make this x2 become 0x2. So we're going to do x2 minus x2. And equation 1 is still the same. Equation 2 is still the same. The third equation is now x2 plus x3 minus the quantity x2 plus x3. So you know that's going to be 0. We're doing x2 minus x2, x3 minus x3. So we get 0 plus 0 equals 0 minus 0 on the other side is also 0. And at this point, I guess maybe we should clear away this 3x2 here as well. So to get rid of this 3x2, just to say we're following the steps, we still need to clear x2 from the other equations other than the second equation. We want to do this 3x2 minus 3 times this x2, right? And it was good that we cleared away the x1s here earlier because we don't want an x1 to mess up that nice x1 we already have here. So we're going to take, we're going to replace equation 1 with the sum of itself and minus 3 times equation 2. So that's going to be the new equation 1 is now x1 minus 3 times 0, which is still x1, which is what we want. And then we're going to do 3x2 minus 3 times x2. That's 0 x2. And then 0x3 minus 3x3 will be minus 3x3 equals 2 minus 3 times 0, which is 2. And equations 2 and 3 are unchanged. Okay, so this is now as reduced as we can get it, as we've eliminated as much as we can. There's nothing else we can eliminate with x1 because there's only one equation with x1 in it. There's nothing else we can eliminate above or below x2. And we can't really do anything better with the x3 because if we were going to try to cancel out this x3, we would just be going backwards. We would then have another equation that has x2 in it. So yeah, there's nothing else we can really do. There's no x3 down here that we can do anything with to cancel out these x3s. So yeah, we're stuck. And at this point, we can sort of see that x3 can be any real number. Like a preview of where we're going in the next section is we can say x1 equals 3x3, x2 equals negative x3, and x3 can be anything. So some solutions are, for example, if x3 is 0. Oh, whoops, I lost a 2. This was supposed to be 2 plus 3x3. So if x3 is 0, x1 will be 2, x2 will be 0, and that's one solution. Another one is if x3 is 1, x2 will be negative 1, and x1 will be 5. If x3 is e, x2 will be negative e, and x1 will be 2 plus 3e. So there's an infinite number of solutions. It's definitely consistent. Okay. So yeah, that is a little extra practice with those. The solutions to all of these are on the second page at the bottom, but don't peek. Or you can peek if you want to. Of course, it's a good idea to check your answers. And yeah, so I hope you're having a good long weekend, and you still have 1.2 stuff to do for Wednesday. And if you want to do that first or do this practice first, either one is good. So I will see you later.